We are going to finish up talking about the mechanisms of heat. We talked about what they are, but I'm just going to go through it a little more, and then get into some of what we call thermodynamics, talking about the processes of heating, cooling, and how they affect life. So, going over who I don't see. Okay, James just showed up, and Brittany just came. I don't see Trace, Gila, or Alex. All right? Okay, first clicker question. From Friday, which material is the best insulator? Copper, iron, air, or wood?
That's cool.
Yeah, that would be. You weren't seeing anything I was doing either. Well, you know what other people are answering. They could have been wrong. Nah, that's not possible. You also could see who it was that was answering, so you could see who was quick and who wasn't. Still not in, Corso. No. There you go. Irving. Okay. Brittany, you're logging in?
Yeah, sorry.
Okay. While Brittany is logging in, Alex, did you answer before you entered the room, Alex?
No, I answered this before.
Okay, I was just looking and saw that you were answered already. You're the one that gets to answer this with everybody. And Brittany has answered now. So we had 0, 0, 20, and 1. So Alex, tell us about your answer and your reason.
I just remember hearing at some point that air is the best insulator. And we don't insulate houses with wood, we insulate it with stuff that has air in it, so I just figured it was probably better.
Okay, I'm going to go with this first one. He just remembered hearing it. Because in class on Friday, I said air, and why do we use down? Trapped air. Why do we use spun fiberglass? Trapped air. Because air is a really good insulator. Wood would be your second best option. Wood is reasonably good. Iron, that's a really poor insulator. And copper is a really horrible insulator. Heat travels through copper better than almost anything. It's a good conductor. So copper is a great conductor. Iron's a pretty good conductor. Wood is a very poor conductor. And air, really no conduction at all. So conduction is just the opposite of insulation. Now, I spoke briefly about convection. Didn't have time to really talk about these things. But just think about, let's say you are lucky enough to live at Huntington Beach, California, which is where my sister lives. So here we have the beach, and here we have the ocean. And the ocean temperature is really quite stable. Why would the ocean temperature be quite stable? We have good physics knowledge now that can answer that. Why doesn't the ocean temperature fluctuate a lot during the daytime or nighttime? Such a large mass is part A, but something like Half Dome also has a large mass, and its temperature fluctuates a lot. So there's another portion to it. But that is part of it. Don't think that he's wrong. He's right. That's part of it. Okay, it has a large specific heat. The specific heat is the number that relates how the temperature changes when it absorbs heat. And so water has a large specific heat. And remember, Q is equal to MC delta T. So if C is large and M is large, what really matters is M times C, something that we call the heat capacity. And so if M times C is large, then a huge amount of heat times a large MC means a small delta T. So water we call a thermal reservoir because it will keep roughly the same temperature regardless of its environment. And so the water, the ocean water, depending on what time of year you're there, is going to remain somewhere around 50 degrees Fahrenheit. Now, at nighttime, you don't have the sun shining on the ground. Radiation is transfer of heat through electromagnetic rays. Light from the sun is electromagnetic ray that is warming the ground during the daytime. But at nighttime, that's cut off, so there's nothing heating the ground. But the ground is still giving off heat, and so the ground cools. So at nighttime, the temperature of the ground may move to temperature night is equal to, let's just say, 40 degrees Fahrenheit. So it's colder over the ground than it is now. 40 degrees Fahrenheit is pretty cold. Huntington Beach, another place, but it might be 40 degrees Fahrenheit there. It's hotter over the water than it is over land. And because it's hotter over the water, the air that is over the water is going to be less dense than the air over the ground. And what happens then is this less dense air floats up, and this more dense air takes its place, gets heated up, and floats up. And so you create a pattern of the air circulating like that. So in the evening and early night, you'll have air flowing from land out to sea. In the morning, though, the sun shines on the ground, and what happens to the ground? It heats up. And so the temperature in the daytime for the ground might be, let's say, 70 degrees Fahrenheit. Well, because the temperature is 70 degrees Fahrenheit, the air over the land expands more, is less dense. That floats up, and you reverse the cycle of the breeze. So those coastal breezes are completely driven by convective currents. Convective is the transport of heat through an intermediary. In this case, it's the air itself is the intermediary that's transporting heat either from the ground to the water or from the water to the ground. And if you study meteorology, that's a big part of everything that goes on with weather. You heat up the air, it becomes less dense, it floats up. So it's full of very useful things. You know what we're not full of? We're not full of equations for convection. So if it comes to the test and you have a question on convection, it can only be in A, defining what convection is, or B, explaining how convection works, because you don't have any actual calculations you're going to do with convection. I left this slide in kind of out of place. What is the purpose of hair? Now, I'm a creationist. I believe God created us with hair, and some of us have more body hair than others. I won't show off right now. But evolutionists will say, our body hair is, now the word goes away. I was going to say redundant, but of course that's not the word. But it's unnecessary. But it was necessary for earlier versions of the human before it evolved. Why? Because the hair or fur, which, yes, if you were to look at my chest, you'd probably say, yeah, it's fur, that's not hair. It traps air. But what does it do if it traps air? Air is a good insulator, and so it helps us to have heat flowing out of the body at a slower rate. Now, of course, I look at Corso and I'm all jealous because he traps a lot of heat in his hair, except for on the side where he got a little tight. Me, right up here, I trap nothing, right? That means I'm losing more heat through my head than I should. I can always wear a cap. But that's our understanding of the purpose of hair, why God created us with hair. Something really interesting, we'll talk about this later when we get to talking about light, but polar bears. What color is a polar bear's skin? Black. What color is the material that the polar bear's hair is made out of? Clear. Why do you look at a polar bear and think it's white if it has clear hair and black skin? It's air trapped in it. Its hair is hollow. At least this is what I've read. Its hair is hollow, so it's like a little tube. And so you have air trapped there in the hollow hair, giving it better insulation. And we're seeing the light scattering from those little tubes of air that gives us the white color. It's me scattering, the same reason that a cloud looks white. Me, by the way, that's a Chinese name, just in case you are wondering what me scattering is. Me scattering occurs when you have the thing that light scatters off of is longer than the wavelength of light. If the scattering center is smaller than the wavelength of light, then you have Rayleigh scattering. Rayleigh scattering scatters different colors with different efficiencies. This is all stuff we'll have second semester. But if you look at the sky, you're seeing sunlight. What color is the sun? The correct answer is essentially white. It doesn't look white if you look at it. Until you go blind, it looks yellowish. But that's also an artifact of this Rayleigh scattering. The Rayleigh scattering is much more efficient for blue light. And so we have that white light from the sun. If you don't look directly at the sun, it's scattered by the atmosphere, and it scatters blue a lot more than it does the other colors, so you see the sky is blue. The sky is blue. Okay, that was a non sequitur, something we'll learn next semester. Radiation. The last mechanism of heat is radiation. And radiation is giving off energy in the form of electromagnetic waves because something is hot. Once again, second semester, we'll talk about black body radiation and Planck's quantum hypothesis, followed by Einstein being the true believer, saying that indeed materials give off energy in quantized amounts called photons, particles of light, and it explained this curve. But back before anyone understood that was 1905, that's the beginning of modern physics, they knew that things gave off energy, heat, because they're at a high temperature. So you can bring your hand near something and you can have a vacuum, nothing between there at all for conduction or convection, still receive the heat. Because after all, that's what's happening from the sun. There is no contact between the sun and us. Hence, there can be no conduction. And it's vacuum between us and the sun, to a good approximation. Hence, there can be no convection either. So it's all radiation. The only warming we can get from the sun is radiation. And so the power for radiation has a bunch of terms in it. Sigma. Sigma is the Stefan Boltzmann constant. That's an E. I think it's two N's. And actually, can somebody look that up? Because I actually want to use it in just a moment. This script E is the emissivity. The emissivity is a number that tells you how efficient something is at either emitting or absorbing radiation. The emissivity is the same for both emission and absorption. It doesn't change. But it does depend on the properties of the object. Something that is black is a perfect emitter of radiation. It's also a perfect absorber of radiation. Hence the term black body radiation, because that's the perfect situation. Something that is white is a very poor absorber or very poor emitter of radiation. And of course, what's the poorest? The poorest is something that is reflective. So this here has a mirror finish. That's to give it an emissivity that's very close to zero. It's a very poor emitter, very poor radiator. That emissivity then has to do with color. if we were to take, okay, Brittany's wearing a black sweatshirt and Noah is wearing a roughly white coat. If Brittany and Noah go out and wear those on a bright sunny day, who's going to absorb more radiation? Brittany will. Why? Because the black shirt or sweatshirt is a much better absorber of the radiation. Now, if it's a bright sunny day, she's going to be receiving a lot more radiation than she's going to emit. We'll do a problem on that in just a moment. And so she would warm up more than Noah because of the different color clothing. So, that's something that, let's say you're a football team. You might know that the standard is you wear your colored uniforms at home and you wear the white jerseys when you're on the road. But teams do have the choice. And when the Raiders go to play somewhere that they have an outdoor stadium and it's a hot, sunny day like 90s, the other team will choose to wear their whites and make the Raiders wear their blacks. Why do they do that? Because the players are going to get hotter. They're going to get more physically exhausted because their bodies are hotter because the jersey's absorbing more sunlight. And so teams will use that as a strategic thing. There's still questions about how effective it is, but it's a good theory. And then there's always the Denver Broncos. The Denver Broncos went to San Diego, and San Diego had announced that's what they were doing, that they were going to make the Broncos wear their dark jerseys, and San Diego was going to wear the light ones. But this was when Mike Shanahan was there. He just didn't bring the jerseys they were supposed to wear and then said, well, what can we do? These are the only ones we brought, and guess what? We're at your home. You have both. Which, I would have considered major cheating. But anyway, that really happened. My team wasn't involved, so I'm not super upset, but it's still annoying that people cheat. Okay, so since radiation works the same for absorbing and, I didn't finish the things in the equation. The next two are simple. A is the surface area. And of course, T is the temperature. What units will you have to use for temperature? Have to use kelvins. Why is it you have to use kelvins and you can't use Celsius? It's not a change, it's the actual temperature. Now, if you look at the power for radiation net, then it has temperature of the object to the fourth minus temperature of the environment to the fourth. Can I use Celsius then? Because that's not a change in temperature raised to the fourth power. It's temperature of the object raised to the fourth power minus temperature of the environment raised to the fourth power. The difference in the fourth powers is far different than the fourth power of the difference. So you have to use kelvins. It's absolutely mandatory. So let's just do this problem. You, with an emissivity of 0.97, have a surface area of about 1.9 meters squared. I looked up those numbers. Those are averages for a human. And you have a body temperature of 37 degrees. Oh, man, what did I forget to put? Yeah, you've got to put the units. If you don't put the units, it's useless. Something you should have learned in lab. Something you will definitely want to know for tomorrow's lab final, right? Because units is a really important thing. What is can you read the rest of that? What is your rate of radiative heat gain / loss in a 90 degrees Celsius sauna? Okay, so you're in a 90 degrees Celsius sauna. Are you going to be absorbing radiation from the sauna? Yeah, because it has walls, it has an environment that's at a higher temperature than you. Are you going to be emitting heat? Yes, you'll also be emitting heat because your body temperature is not absolute zero. As long as your body temperature is above absolute zero, you know what? That means everything. Then you're going to be emitting as well. And so to find the net, we're going to take the difference in the two. Did you have a question, Corso?
Yes, but it's about the lab final.
Yes, but it's about the lab final. Go ahead and ask.
So, after we do whatever we have to do in the single room, is it just like lab that you write out things, or what is it?
Okay, just so people can be prepared for tomorrow, when you come to the lab tomorrow, I will have a piece of paper for you to answer questions on. And you will answer those questions, and then I'll have like 5 different rooms set up for people to do the practical part by themselves. And so I will take volunteers, and you do want to volunteer early. Unless you're slow at doing the writing part, you want to volunteer early. Not everyone can be the first, but it's to your advantage. And I'll tell you what in just a moment. So then I'll take people to a private room where they will do their own little experiment. And remember, the write-up is just how are you going to do the experiment, what's your method, and then what are your measurements, and then your calculations, your analysis. So you're going to go there, and it might take 10 minutes. Some people it takes twice that. After you finish, you'll come back and you'll work on the written paper, and I'll call somebody else. There's only a little over 20 questions on the written test. So the written test will take less than an hour. We have 3 hours of lab period. You've got the practical part that's going to be something around 10 to 15 minutes. If you finish the written paper and you haven't done the lab part yet, you're just stuck twiddling your thumbs, right? Because we just got to cycle people through. And so it's advantageous if you're quick at doing the written test, and you know for yourself if you're quick or not. If you're quick at doing the written test, you want to be one of the first ones to go in so that you have the written test and the practical done and you can leave. If you're slow, you can be one of the later ones simply because you're not going to be disadvantaged by not being early. Question, Jeffrey?
So you have to have the written portion of the test done before you do the practical?
No, you don't.
Otherwise, we'd be here an extra hour.
Right.
Okay, so getting back to this, we want to calculate the rate at which you are going to either gain or lose heat due to radiation. Now, if you think about this, in the sauna, there are 3 mechanisms of heat. Conduction. Will you have conductive heating or heat loss, heat gain or loss through conduction? Okay, we have a yes from Ashley. What's your reason, Ashley? Don't ever call me again or I'll never answer. Okay, you are sitting on a bench or something. And so you have direct physical contact with something, hence you have the avenue of conduction available to you. But you're sitting on something that's a relatively poor conductor. When you sit on it initially, let's say you come in and that surface is at the same 90 degrees Celsius as the sauna, way hotter than your body. So the instant you sit down, you have your flesh touching that wood, because we all know that in the sauna, okay, I never do this, I put a towel around me because I'm modest, but traditionally you're supposed to be in there in the butt. So that's the way we're talking here, you're in the butt. So your skin touches, it's hotter than your skin. What's going to happen with heat? It goes from where to where? From the bench into your body. And it'll keep doing that until what condition is reached? Till they're the same temperature. Well, here's the thing. The wood is a poor conductor of heat. So the part that you touch will conduct its heat into your body and cool down to your body temperature in almost an instant. And then you have very slow conduction through wood to replenish. And so it's very slowly going into your body after that. So when you put your skin on the bench, in an instant you have a reasonable amount of heat flow, and then it just stops for all intents and purposes. It's very slowly coming in. So for you sitting in the sauna, the conduction is vanishingly small. So it exists, but we're going to ignore it because it's vanishingly small. What about convection? What does it take to have convection? Okay, you have to have some kind of a fluid that can transport heat. In the sauna, do you have any kind of fluid that can transport heat? Yeah, that's what a sauna is all about, really. It's about having these little water droplets coming around, transporting heat to you, making you sweat like a fin, right? So you're going to have a lot of of convective heating in the sauna. We're not going to be able to talk about that because we don't have any equations about that. Then we go to the radiation. That's the one we're going to calculate here. So for the radiation, using our equations, the heat gained, well, let's not use the word gained. Let's say heat absorbed is going to be equal to the Stefan-Boltzmann constant times your emissivity times your body surface area times the temperature of the environment raised to the fourth power. So putting in numbers, who looked up the Stefan-Boltzmann constant for me? Okay, so what is the Stefan-Boltzmann constant?
10 to the negative 8 watts meter squared per Kelvin to the fourth.
Okay, is it 5.678?
Yes.
Okay,
I don't know about the 8.
well, it says 5.67. Well, then I must be wrong on the 8, or it would have rounded up to 5.68. Okay, so there is the Stefan-Boltzmann constant. Then we have your emissivity, 0.97, times your surface area, 1.9 meters squared. And then we have the temperature of the environment raised to the fourth. I said that the environment is at 9 degrees Celsius. So what is that temperature I'm going to put here? Now let's just look at the units before I go on. Meters squared, so those cancel. Kelvins to the fourth, kelvins raised to the fourth, so those cancel. And so I'm going to be left with watts because I forgot to put Q over delta T. Right, my equation is for the power and I forgot to put that. So the units will be in watts, which is energy per time. Now, has somebody done the calculation for me?
1846.
Okay, 1846 watts. That's the rate at which you're absorbing heat. Now we want to look at the rate also at which you're emitting. So that's the same sigma, the same emissivity, the same area, but the temperature of U raised to the fourth power. That's where the A is. It's 5.67 times 10 to the minus 8. That's how. And your temperature is 37 degrees Celsius, which add that to 273, that's 310.15 kelvins. So what do we get there for the rate at which you're emitting heat?
966.
It's what, 66?
966.
So if you look at those numbers, you have more heat that you're absorbing than the heat you're emitting. It's a net heating effect, right? Well, that's not good. Your body's going to get overheated. Yeah, I suppose you probably do. So, yeah, I don't know. I've started using the sauna because I have in my head this random hope that somehow it makes my body more efficiently burn calories. I don't know. You know, in this case, it says my body's gaining energy. If you were to think about that very literally, you'd say, oh no, there's calories flowing into me. I'm going to gain weight. But your body can't metabolize thermal energy. So not a concern. Now let's take this and relate it to something very important. We have this Earth. What's the rough temperature of the Earth? Roughly speaking.
2 degrees.
It's how much? Just an average temperature for the surface of the Earth.
2 degrees.
Okay, you have to say it louder because I just see
2 degrees Celsius.
0?
2.
2. Okay. So 2 degrees Celsius, he's saying it's an average temperature. I'm going to go up from that just to get a nice round ballpark number of 300 kelvins. Right, 300 kelvins, that's 27 or so. But it's only one significant digit. So it's the same number to it, one significant digit. What's the temperature of the surface of the sun? It's about 6,000 kelvins. So if we look at the sun, the amount of radiation the sun's giving off is far higher than the radiation the Earth is giving off in terms of the rate. So the sun will lose energy by heating a lot quicker than the Earth will. Now there's some other things we're going to learn, and I have a slide coming up in just a few moments that talks about the whole greenhouse effect and global warming issue. It's an important thing, and it has to do with what we're seeing here. So let's get to that. First, thermographs. You might have seen things like this. This is looking at infrared radiation. When I was a child, I called it infrared because I knew how to read and I didn't know what it meant. Infra means below. So that's light that has a frequency below the frequency of red light. We are giving off radiation, but the radiation we're giving off is clearly not visible. If we turn out the lights, we can't say, oh yes, I see everyone, they glow in the dark. Because we don't see infrared light. But if we could, we'd see them glow in the dark. Hence we have night vision. If you are, a soldier in the right army, you might have night vision goggles. Or if you're, a cutthroat hunter that believes I want to be a long ways away from an animal and just randomly kill them and have no chance of them killing me, which makes it not sport. If you're out there and you're chasing down the deer, you catch it around the throat and you strangle it, that's sport. Not good sport, but it's sport. If you're standing 100 feet away and you've got a bow and arrow or a rifle, that's not sport. That's killing. Okay, but sorry, that's not physics either. So, you're a soldier or a hunter, you got these night vision goggles. All they're doing is using cameras that are sensitive to infrared light and looking at the light that things are giving off because they're hot. They're looking at the radiation. And then they just take that picture and draw a new picture in visible light so our eyes can see it. That's what night vision goggles are. That's what this is showing. So you see different temperatures here as different colors. And so you can look and say, woo, there's a lot of heat coming through that window because of its color. There's not much heat coming through the wall here because of its color. And, there's a lot of heat coming through the walls in this region because of their color. It's useful, especially if you're trying to make an efficient home. Okay, now for the greenhouse effect. The greenhouse effect is a simple effect. The sun gives off radiation, and it's peak radiation because it's hot. The peak radiation is shorter wavelengths. We saw graphs of that, but I didn't focus on it. You can see there the pictures. 3,000 kelvins has a peak at about 1,000 nanometers wavelength. You go to 6,000 kelvins, the temperature of the sun, and its peak is somewhere around 500 nanometers. So sunlight is giving off peak radiation at about 500 nanometers. The Earth, being about 300 kelvins, is giving off its peak somewhere around 10,000 nanometers. So the wavelength, I know we haven't talked about wavelengths at all, so it shouldn't necessarily mean much to you. But the range of frequencies or the wavelengths that the Earth gives off are long wavelengths, whereas the sun's giving off shorter wavelengths. It makes a difference because the clouds, the atmosphere, I should say, is transparent to visible light, and 500 nanometers is squarely in the middle of the visible range. I believe God created us with vision in the same range that he created the atmosphere, so it's transparent, so we can see the universe out there. If we had infrared vision, we wouldn't be able to see stars because the light doesn't get through the atmosphere in infrared. If we had vision in radio wave range, we would also be able to see the stars, but we would have very poor resolution. We wouldn't be able to see details. So we have vision in the range that allows us to appreciate what's out there. If you believe in evolution, you might say that we developed this vision in the visible range because That's the range the light comes in from outside. But that would actually be counter to evolutionary theory. Because evolutionary theory is about survival of the fittest. You have adaptations that make something more survivable, more fit to reproduce, if you want to be exact. And what would make you more fit to reproduce? You're less likely to be killed by a predator. And what kind of vision would make you less likely to be killed by a predator? Infrared, because you'd be able to see them day or night. So evolutionary pressures would push us toward having infrared vision rather than visible. So I use that as surely weak evidence, but something that fits with my vision of God creating us to be, to be able to enjoy things. Okay, so we have solar radiation coming in with an intensity. Intensity is a power per unit area. So power, the rate of energy flow per unit area of roughly 342 watts per meter squared. Now, of that intensity, you have 77 watts per meter squared that gets reflected from cloud tops. So that never gets to the earth. It doesn't do anything. It just is reflected back out. You talk about the albedo of a planet. That's telling you about what percentage of the light is reflected. So we could take this here and say, okay, we have 77 reflected by the clouds and another 30 reflected from the surface. So 107, yeah, that's 107. 107 watts per meter squared divided by 342 watts per meter squared, that gives you the albedo of the Earth, the percentage that's reflected. Then we have 67 watts per meter squared that's absorbed by the atmosphere. So it's making the atmosphere warmer. And the vast majority, 168 watts per meter, I say vast majority. Okay, so that's roughly half. Roughly half of the solar radiation reaches the surface and is absorbed by the surface, making the Earth hotter. Well, the Earth is then giving off radiation. The Earth is giving off radiation at a much lower rate because the temperature of the Earth is much cooler than the temperature of the sun. And then we have that radiation, you notice there, 350 plus 40, so 390 watts per meter squared being radiated from the Earth. It gets up to the clouds, and the clouds that allowed most of the visible light through absorb all but the small fraction, 40, of those 390 watts per meter squared. So the clouds absorb most of the radiation that comes from the Earth because it's in the infrared range. And that's where the greenhouse effect starts. You had radiation comes in just fine. Radiation can't leave. It's a lot like the Hotel California. You can check out anytime you like, and you can never leave. So you have that radiation is trapped in, but then you'll have some emitted from the atmosphere. As the atmosphere warms up, the amount that's emitted from the atmosphere will increase. And of course, you have most of it comes back down to the Earth. And so what happens here is the atmosphere, and with it the Earth, heats up until you have a balance between the radiation, the energy flowing into the Earth, and the energy flowing out of the Earth. And so the temperature of the Earth is set by that balance. So if the sun gets hotter, it's going to give off more radiation. Also, if the sun gets closer, we're going to absorb more. So if the sun gets hotter or gets closer, we're going to receive more radiation. If you have more coming in than's going out, what's going to happen in response? The temperature is going to have to go up, so you have more coming out of those clouds. So that's a natural effect. There is the Milankovitch hypothesis, goes back over 100 years, that says that the temperature on Earth, the global temperature on Earth, is caused by a number of factors such as how hot the sun is, because the temperature of the sun varies, by how close the sun is to the Earth, because the distance between the Earth and the sun varies. It's currently closest to the Earth in January, farthest from the sun in June. Yeah. Also by the Earth's precession and a number of other factors. That has been actually very successful in taking historical data and mapping I think it's 7 factors in the Milankovitch hypothesis to global temperatures as we can determine. But there is another factor, and that's the one that we focus on in today's modern discussions, and that is the atmosphere part. The atmosphere absorbs radiation. Why? Well, we call them greenhouse gases. What's the dominant greenhouse gas? The one that's responsible for, like, I can't remember the percentage, but I think it's like 97%. It's over 90% greenhouse effect. What's the dominant gas? What'd you say? Oh, I thought I heard the right answer.
Carbon dioxide.
Not carbon dioxide. Not methane. That is more than carbon dioxide, but it's less than the predominant one. It's water. Water vapor is the primary greenhouse gas. It's the one that is most responsible for the greenhouse effect. Then you have methane that Rebecca mentioned that is also a very effective greenhouse gas. Then you have carbon dioxide. Why do we talk about carbon dioxide? It's one that we directly affect, and it doesn't make people who eat meat angry. Right? Methane, if we didn't raise beef, there'd be a lot less methane in the atmosphere. My alma mater, Washington State University, did the original seminal research measuring how much methane is produced by cattle in their flatulence and in their belching. They actually did that. They put little things to collect the gases coming out of both ends of the cattle so that they could determine just how badly they're affecting the environment. And everyone knows, if the whole world everyone knows, everyone in science knows, if the whole world converted to being vegetarian, no one would be talking about not anthropomorphic, whatever it is, anthropogenic global warming. Because if we all converted to vegetarianism, the greenhouse gases that we produce would no longer be a problem. But nobody wants to convert to vegetarianism. So they focus on the other one, that we have a big effect on carbon dioxide. Now, carbon dioxide is indeed a greenhouse gas. Is it saturated? Most people say no, some people say yes. One thing that you really should know about carbon dioxide, the Earth has a liquid surface and livable temperatures because water absorbs carbon dioxide. And then it leaves sediment of like calcium carbonate. It makes it into rock. So the carbon dioxide gets turned into rock in water. And the Earth having liquid water, it will absorb carbon dioxide and deposit as rock. But as temperature increases, the water will not hold as much carbon dioxide. And so paleo-environmentalists, people who are looking at the composition of gases and the temperatures, will look at how much carbon dioxide is in the air, like you find a trapped bubble, to determine the temperature. They use it as a proxy for temperature. The higher the temperature, the more carbon dioxide in the air. And now we're turning it the other way and saying, but the more carbon dioxide, the higher the temperature. The two work together. And so there is a certain amount, if the temperature is getting warmer, we should have more carbon dioxide in the air. Maybe the temperature warming and the carbon dioxide, it's, the raise in temperature cause the more carbon dioxide. It's not a 100% one direction calculation. All of this I tell you because I am one of those fringe elements who thinks we don't have enough evidence to say with a certainty that man is responsible for changes in our global climate. But staying on point, I'm also a Christian who believes that man has a responsibility to take care of the planet. So we should be taking care of the planet even if we're not causing a temperature change. One last thing on this, because I'm really on my soapbox. The Earth has been in an ice age. We have warmed up to pretty much the average global temperature now historically. So we're not in a hot region right now. We're coming out of a cold region. But it's the temperature regime that humans have lived in, and thus we're worried, what if we go to the other temperatures the Earth has been? Okay, let's move on. What would happen if there was no greenhouse effect? Okay, Corso, Brittany, nice. It's down to you, Corso. All right, we're all in. 1, 3, 17. Good. I didn't go to this. This required you to use your previous knowledge and or your reasoning. The earth requires, okay, I'm not calling on somebody. The earth requires a greenhouse effect to make it livable here. Without the greenhouse effect, it'd be too cold. We'd all be popsicles. You can't live that way. So we require greenhouse effect. There was a commercial from some company, it was probably 6, 7 years ago now. I was just so appalled. They're talking about their vision for the future. And one person is, I envision a future where there is no greenhouse effect. I'm like, okay, well, I like to live on Earth, so I'm not with you on that vision. And of course, that's just because they didn't really understand the greenhouse effect. It is vital. Without the greenhouse effect, we're like Mars. Temperature gets nice and comfortable on Mars, and then it goes to popsicle and then some, right? You would be frozen solid on Mars at night. That would be bad. Venus is the other side of the coin. Venus has a runaway greenhouse effect. Venus is too hot. It'd melt lead anywhere on the planet, anytime, because it has too much of a greenhouse effect. Also, Venus is close to the sun and Mars is farther away, but the greenhouse effect, I believe, is the premium thing that makes that occur. Why is Venus that way? Because Venus never got cool enough for liquid water, so it never took the carbon dioxide out of the atmosphere to put it in the water to trap it away. The Dewar. I have here 3 versions of a Dewar. This one here, your great-grandpap probably went to work and had one of these in his lunchbox filled with nice cold milk. I don't know, did you guys use these when you were kids? Were they glass like this? No. They were when I was a kid. And so every 3 months or so when I would drop my lunchbox, it would break and you shake it and you have the glass rattling everywhere. And then you know that the Dewar is busted. You got to go replace it. So a thermos is a brand name for a Dewar. And it's supposed to have a cap on here. I don't have a cap. I just have a little cup you drink out. Here's what we use in the physics lab regularly. We have the tape that's so lovingly been applied so you can hold it better, it's less likely to slip, etc. Here's what is inside this thing. So this is the Dewar, the basis of it. Now if you look at the Dewar, ready? Go ahead and tap it. Of course, lightly, you don't want to break it. What do you notice? It's hollow. It's hollow. It has evacuated, well, it is evacuated between 2 double walls. So you can see here, they put it in a vacuum system, and then they heat it up, and they turn it, and they slowly pull it off until they close it off. And so now it's trapped vacuum in here. Vacuum means no air. What would no air have to do with heating? There's no conduction because there's no direct contact, and no convection because there's no fluid to flow around. So that trapped air between the double walls stops conduction and convection. If you want to have conduction from inside to outside, it has to go along the edge and come back around. So it has a very large distance. The glass is thin. Remember, conduction rate has to do with the length it has to travel. The longer the length, the slower the conduction rate. And the cross-sectional area. So make it thin makes the cross-sectional area smaller, slower conduction. Glass is a good insulator, so there's very little conduction. There's no convection. And then it's coated with silver, or aluminum more likely. Why do they coat it with the silver or aluminum? That makes it reflective, and that stops radiation. So this is designed to block all 3 mechanisms of heat. Thus, I put something hot in, and I put the appropriate lid there, and it keeps the hot thing hot because no heat can flow in or flow out. Or I put something cold in, I put the lid on, keeps the cold thing cold because no heat can flow in or flow out. And if you put both your ice cream and your hot pizza in, like the old blonde joke, no, that's not going to work because heat can flow between the things inside. Question?
So what about metal?
What about the metal? Can you be more specific?
Whenever they're made out of glass. How does that work?
Well, this is made out of glass with a metal coating
Okay.
that's super, super thin. Because it's so thin, its cross-sectional area is vanishingly small, hence virtually no conduction to that. Was that the question? No?
Like, a hydroponic. Is there glass in that, or is that just metal?
The glass and what?
Hydroponics.
It's a thermos.
Is that a thermos?
It should be like this, but I don't know that specific one, so I can't speak directly.